the penultimate day, 7th day, and probably we'll take one more class on reviewing the question and answers if you want. So we are almost at the end part of our syllabus, and that part reads like box of finite depth, barrier and tunneling problem. So tunneling problem, we will see that it is something very quantum. That means there is no classical analog to this phenomena. So we will understand through examples what tunneling means and how it can be used in chemistry, how it is useful, and the physics and mathematics behind this tunneling. That also we will see to some extent. Maybe we will skip some of the mathematical details, but the physical outline, what's really happening over there, that we will of course go through. Box of finite depth. Box means potential box. We are very much familiar with the one-dimensional box problem, right? So here the heading is the particle in the finite depth box. And as you know, a finite depth box is more realistic than an infinitely deep box. We have studied in our UG classes, particle in a box. You do remember that in that case, the particular box was, the design of the box was like that, at the two end of the box there are infinite potential, right? V is equal to infinity, and inside the box there was no potential, that is V equals to 0. But here the potential is not infinite, rather it is very high maybe, but finite depth. So that is something different from the so-called particle in box problem that we have encountered in our UG curriculum. And why I am calling it, it's more realistic, because in reality in different modules there is no such really such system which corresponds to some infinite potential, right? So wherever and whatever you see, it is finite. Infinite is very awkward number, you know. But why then we still studied the particle in a box with infinite potential? Because it is the simplest model to start with, to understand the whole lot of quantum features. So in the UG curriculum, that's why we study such a simplest model to understand that how quantization happens, what is normalization, how the wave function looks, etc., etc. And we have revisited whole things in our earlier classes, when we tried to visit that how the postulates can be understood in terms of the particle in box problems. So we revisited again, but here we are going to start something new, that is a box, of course, but box of finite potential, finite depth box. Well, the structure of the box is like this. It's the figure. So you see the length of the box is say minus a by 2 to plus a by 2. So this is the box where the potential is actually 0, like the earlier case. So Vx is 0 when x is in between minus a by 2 and plus a by 2. But the second line, Vx is not infinity, unlike the previous case. It is some constant value V0, whatever it is, but it is not infinite. So either x greater than a by 2 or x less than minus a by 2. In both the sides of the box, the potential is finite constant. So this is the structure or design of the box. Now we have to consider the quantum mechanical treatment for this kind of box. Naturally, we will start with Schrodinger equation. So the equation looks like this. Inside the box and outside the box, we will write separately because the potentials are different in these two regions. So inside the box, since Vx is 0, so d2 psi dx2 equal to minus 2 me by h bar square psi x. It's as simple as that. But outside the box, of course, V0 is there, it is not 0, neither infinity, so it is V0. So we have to incorporate this V0 in the equation. So these are the two Schrodinger equations for two regions, inside and outside. Now, unlike the previous case, since V0, that means this constant value, is not infinity, but less than infinity, that's why the amplitude of the eigenfunctions need not be 0 at the ends of the box. So because of that boundary condition, in the earlier case, PIB case, the potential must vanish at the wall, right? But here it is not the case, because simply because V0 is less than infinity. So it is not necessarily 0 at the wall, and as a result we will see something new happens, and that's how it is connected to tunneling. Later on we will see. And outside the box, that is outside the box, so suppose a particle is there whose energy is E, and that energy is less than Vx outside the box, the eigenfunctions decay exponentially with distance from the box, as we will show next. What does it mean that exponentially decay? So it picture says you that here it is not necessarily 0 at the wall, as you see here or here, and then inside the barrier, so here the constant potential is there. Inside the barrier the wave function decays exponentially, it decays fast exponentially, but it is not 0 unlike the previous case. Okay, so outside the region, in the yellow region, you see here the caption, allowed energy levels and corresponding eigenfunctions for a finite depth box. So and one more line here, you see the energy eigenfunctions for a finite depth box extend into the classically forbidden region. So this yellow region is as usual it is called the classical forbidden region. That means classically you cannot think of the particle anywhere inside this yellow region. If the particle is dropped in such a box, then the particle would remain in the box all the time inside the box. There is no way, no possibility of having any chance of having the particle outside this box in this region. That's why we call it classical forbidden region. But here we see the wave functions, though it decays very fast, but little bit of amplitude is there in the yellow region, that means classically forbidden region. So that is something to note, interesting, unlike classical picture. So now the solving the equation, Schrodinger equation, we have set up the equation. Now of course we will skip the mathematical details of solving the equations, but if you see the results, initially as solution of Schrodinger equation we get two set of equation. One is for right hand side of the box, that is x greater than a by 2 right hand side, and another is x less than minus a by 2, that means the left side towards minus infinity. So these are the two wave functions. You must not ask me the questions, sir, how did you get these wave functions, because I am skipping the mathematical details of solving the equation as such, but that is not important. Important is to analyze the function and to go further a little bit. And here the kappa, this kappa is given by this kind of quantity. So what are the parameters in this expression? So kappa is an exponential factor which is actually depending on V0 and E. That means the particle energy E, the potential, constant potential at the barrier, that is V0, my m is the mass of the particle, and this is the constant h bar. So depending on that, kappa is defined. Now you see here is a paragraph to understand these two equations a little bit more. I am reading it out. The coefficient AB, this A, B and A prime, B prime, these are the four unknown coefficients we get as a solution of Schrodinger equation, but they are yet to be determined. Because psi x must remain finite for very large positive and negative values of x, B and A prime must be 0. So let us understand B. If B is not 0, then you see x less than equal to infinity. So if you put infinity here, then it will be e to the power infinity. That means the whole thing would be infinite. But the function must be finite, right? Everywhere. That is the first postulate. I mean the well-behaved property. So that itself, that well-behaved criterion itself demands that in this equation B must be 0. B, of course, B is there as some value, but that value is 0. Okay. And similarly, by same argument, A prime has to be 0 because here it is minus infinity. So if you put e to the power minus kappa minus infinity, that means again e to the power infinity. So again it would be, the whole thing would be infinite unless the coefficient itself is 0. So by logical argument and applying the well-behaved criterion of the wave function, we can easily establish the first two facts, that B is 0 as well as A prime is 0. So we require that psi x and psi dx are continuous at the box boundaries. Now next point is that we need something more from the functions, these functions, as we got, that the function itself psi x and its first derivative are continuous at the box boundaries. Okay, this is again nothing new, because we have seen in our FICS, that is finite integrable continuous and single valued criterion. This is one of the criteria, that the function and its first derivative must be continuous, and here again some logical explanation is there that why they should be continuous. The same thing is happening here also. So let us see what next. The picture that if you plot these wave functions as a distance of the particle from the box, then you see, okay, the caption goes like this, that a decrease of amplitude of the eigen functions as a function of distance from the center of the box. So if you just take one variable as the distance from the center of the box, either side, left or right, then because of the very functional nature, you see A is non-zero, B prime is non-zero, so minus kappa x, so it's a kind of radioactive decay. So the graph looks very similar or close to that radioactive decay of first order kinetics. That means here it is the scale wave function versus the distance. Okay, so that we can that much we can say from the expression itself. Okay, now one more thing, the allowed energy levels and the corresponding eigen functions for a finite depth potential are shown in figure. The yellow areas correspond to the region for which okay, I have already mentioned that yellow region, that classical forbidden region. Now E potential is greater than E total. If you start with this, that E potential energy is greater than E total, that means the potential is V0, and E total, suppose the energy of the particle is less than that V0, then E total is kinetic plus potential. But since potential is greater than E total, that means kinetic has to be negative, right? So E kinetic has to be negative in this situation, in that region, in the classical forbidden region, and for a particle kinetic energy is p square by 2m. So how it can be negative? Because it's a square term, p square by 2m. And the answer is, it is possible that it is still negative E kinetic, because if you assume that P itself is imaginary quantity, that is then possible. So it implies that E kinetic implies that the momentum is imaginary. So for this region, kinetic energy is negative, less than 0, and defines what is called the classically forbidden region. So that I have explained in terms of the figure, and one more information we are getting here, that the momentum are imaginary quantity. Another paragraph, let me be patient enough to read it out and try to understand. Two major differences in the solutions between the finite and infinite depth box are immediately apparent. So we are now in a position to compare to the box problem that we have come across in the UG level, that is PIB problem with infinite box potential, infinite depth box, and here we have studied skipping the mathematical details, but we have seen the picture, the box with finite depth. So what are the differences? First, the potential has only a finite number of total energy eigenvalues, which correspond to bound states. In PIB box, actually there are infinite number of energy levels, because the box itself is of infinite depth, right? But here the depth is finite, so naturally we will get a finite number of discrete or quantized energy levels or states, and it depends, of course, the number depends, how many you will get, that depends on the design of the box, partly the mass of the particle, partly the length of the box, and of course the height of the potential box V0. So M, A and V0 are the parameters on which it depends that how many bound states you will get, not infinite, of course. This is first. Second difference. Second, the amplitude of the wave function does not go to 0 at the edge. That I have already mentioned, that it is not necessarily that at the wall the amplitude is 0 like the PIB case. So it is not 0. Then what? We explored the consequences of this second difference, that is the potential is not 0 at the wall, as the consequence of this second difference when discussing tunneling in next section. So actually, as I also earlier mentioned, that this is somehow connected to what we know as tunneling problem. What is connected? That itself the fact that at the wall the potential amplitude, wave function amplitude is not 0. In fact, we have seen the mathematical expression as well, that itself shows clearly. As in the figure, the fall off of the wave function outside the box is not the same for all eigenfunctions. Okay, it is not 0, but then what value? And it gradually decays, and the decay rate is different depending on some factors. So it is not necessarily that all the same. If for all the levels the picture is same, no, it falls off. Of course, the wave function falls off rapidly outside the box, that is in that yellow region. But the fall off rate is not the same for all the states or levels. How? Psi x falls off most rapidly with distance for the most strongly bound state. So strongly bound state means a very lower state. So when V0 is much greater than E, that means the particle has very low energy than the depth of the box barrier. So that means at the very lower part of the box, and in the potential and most slowly for the least strongly bound state in the potential. So what happens? For the lower levels it goes very fast off, and for higher levels as E increases and approaches towards the box barrier height V0, then it most slowly for the least strongly bound, that means the higher levels. So that means okay, what that means, that we'll see from the following figure. It will be very clear. Yeah, this is the figure. So for example, this is okay, 1/4 V0. Here it is the V0 height, and you see it's much lower level, almost 1/4, 25% of the height of V0. That means E is much less, and here E is very close to V0 because it is 3/4 of V0, the higher level. So in the lower level, this region, it falls off very fast, so fast that at this barrier, okay, the box structure is slightly different, I will explain here later on. So it is fast. Now it is so fast that at this point it has already become 0 almost. But since with energy high the falling off rate is not that high, so it slowly decays, and at this point it has some amplitude and not equal to 0. So that is the case. Okay, and this barrier is slightly different from what I started with. Here let us explain with figure that the structure of the box. Vx is 0. Here Vx is 0. Where? When x less than 0. So x less than 0, here Vx is 0 outside, here Vx is 0, and for x greater than a, here also the right hand side it is 0, and what is inside, that is between 0 to a, the second line, when x is between 0 to a, then it is V0. That means in the earlier case and the present case, actually it's like a box you have just inverted, that kind of thing, right? So this is, but anyway it looks like a barrier, as if a particle is coming from left, okay, and it faces a barrier of potential, then what would happen? That is the question. Now I am going to discuss the tunneling problem. So how it defines? A particle can escape through the barrier even though it does not have sufficient energy to go over the barrier. So suppose you are a high jumper and this is the height of the rope, right, or rod, and if you don't have sufficient energy to go top over the barrier, you cannot go over that region, right, over the barrier to that right side region, you cannot go because you are a classical particle. So energy, if it is greater than V0, then of course it can cross the barrier and go to the right hand side. That is the classical picture. But the quantum picture suggests that even if the energy of this particle is less than the barrier energy, that is V0, so classically it is not supposed to go cross the barrier, but it can go to the right hand side, not really crossing the barrier but tunneling through the barrier. We call it tunneling through the barrier, as if আমরা একটা টানেল খুঁড়ে দিয়েছি সুড়ঙ্গ through the barrier. So that's why a particle, okay, it doesn't bother about to jump over the barrier because it knows how to go inside the tunnel and through the tunnel to the other side of the barrier. So that is the tunneling. Simply speaking, that is the tunneling case. And why it happens so? That is simply because psi is there. If psi is there in somewhere, then psi square is there, and psi square is probability density. So that means probability is there. Probability of what? Postulate 1 says that psi square or mod psi square gives you the probability of finding the particle. So if psi is there right hand side, then psi square is there. That means probability density is there. That means probability is there. That means you have some probability to find the particle in the restricted, which was restricted classically. So tunneling in which a wave particle can pass through an energy barrier, and it has no analog in classical physics. So it is possible because of its basic, fundamentally because it is dual. That's why a particle is not just a particle in quantum mechanics, but it's a wave and particle dual. So when it passes through the barrier, it no longer remains or behave as a particle. Actually, it can penetrate the barrier as a wave. So that is the thing fundamentally. Okay, so that is the picture of what I mean by tunneling, and then I will show some of the cases, example cases. Well, here I was talking about that the lower energy and the higher energy, that means 1/3 of the V0 or 3/4 of the V0, and then we were comparing that how fast it will decay inside that region, and at the wall, finally at the wall, when it does reach the right hand side wall, then whether it has already become 0 or it has still some amplitude remaining. This comparison I was doing as far as the energy of the particle is concerned. So here quantitatively we can see that actually that depends on this quantity, h bar square by 2m V0 minus E. Now if you just analyze this portion, you can understand that suppose E0 is much less than V0. Okay, so E0 much less than V0 means this quantity would be very high, and this is in the denominator part. So if the denominator is quite high, then the overall result would be very small, right? So that is the thing, and just the opposite happens if E0 is very close to E is very close to V0, that means E is quite high, then the difference is very small, so the denominator is small and the overall result is very high, right? So that's all about. Let me read out the whole paragraph. That it shows that the tunneling is much more likely for particles with energies near the top of the barrier. Why? Because in the top of the barrier, as I mentioned, that it slowly decays. So at the right hand barrier, it still has some amplitude, which we can extend to the even after the barrier. But if it has been so that at the barrier it decays so fast, and at the right hand side barrier it has already become 0, so there is no way of getting any further psi on the right of the barrier, right? And that slow decay and fast decay, as I mentioned, that it slowly decays for the higher energies. So that's why tunneling is more likely for that energy levels. So I again repeat that tunneling is much more likely for particles with energies near the top of the barrier, and that is that you can get it from this equation as well. So here is a graphical representation of the picture. It's energy axis, particle energy, and it's the tunneling probability for different barrier width. As you know that there are mass A, the length of the box, and the V0, all three are important. So if we vary the A value, that means barrier width, then our picture will be different. So suppose for a given barrier, barrier is high, quite high, but for any barrier the pattern is the same, that means it is increasing slowly, increasing upwards, okay, for all the okay. For barrier width, of course the graphs will be different from one another, but the pattern is the same. Now what is the pattern? The tunneling probability, it increases with energy of the particle, as I explained in this paragraph also, that as E goes high and high, then tunneling probability would be high, because rate of decay inside the barrier would be low, right? Rate would be low. So that is the qualitative and at some extent quantitative explanation, that what first of all what tunneling is, the basic physics behind it, I mean quantum philosophy behind it, that is clear qualitatively. Then with a little bit of quantitative expression, we could understand that the falling of a function inside the box, and then what would happen at the right hand side barrier, and depending on that, if it is quite high still, then tunneling would be more likely, and the other case reverse would be happening, okay. Now a problem is there, example problem, and the whole solution is there. So don't bother much about the right hand side initially. First let us try to understand the problem. As was found for the finite depth well, the wave function amplitude decays in the barrier according to this function. That's why I discussed this formula, you know? Decay. So according to this value, this function, this part, decay rate would be controlled. So it says that the amplitude follows this expression. This result will be used to calculate the sensitivity of the scanning tunneling microscope. Assume that the tunnel current through a barrier of width A is proportional to psi x square, or mod A square is this. So you know, all of a sudden I in this problem I uttered or raised some word, scanning tunneling microscope. So probably all of you have heard this word, scanning tunneling microscope. Often we call STM. It is really a very sophisticated instrument, medical instrument, and it's gifted by quantum chemistry, and it solely depends the functioning, working functioning of this instrument. It depends solely on a beautiful quantum phenomena called tunneling. So this instrument really makes use of tunneling. Had there been no tunneling, there had been no scanning tunneling microscope, right? So later on, if you are interested, you can go through this problem. What really the equation is very simple, but I am not going into the details of this this type of problem. Neither I advise to focus it as far as exam is concerned, but for your further understanding, of course, you can study. Well, this potential, can you identify this potential? Now we are switching over from box to another kind of potential. It was V equal to constant, right? But here V is function of x, not constant, and the simplest possible x dependent potential is the simple harmonic oscillator. So of course you can identify this potential as the half kx square type potential. Not type, it is really half kx square parabolic function, and this represents the simple harmonic oscillator. Now what happens if you have studied a lot SHO problem, and you know the energy expression, you know the energy quantization, you know the equal spacing of the energy values, you know the wave functions, Hermite polynomials, how to draw the graphs, what it looks like, etc., etc. In fact, in third year, BSc third year, you have studied the spectroscopy, right? Vibrational spectroscopy, and that is nothing but an application part of the quantum theoretical part on SHO or enharmonic oscillator. That much. Like the rotational spectroscopy is nothing but the quantum application of the theoretical part of rigid rotor problem. Similarly, vibrational spectroscopy is nothing but the SHO related or enharmonic related problem. So, what I mean that you have got a lot on these things SHO, but probably we have missed one or two finer points after getting this diagram. These are nothing but the wave function as such, not the square of wave function, but the wave function. You know, negative, positive both are there. The number of nodes is increasing gradually, and you know that the kth state has k number of nodes, and k starts from 0. Unlike the PIB problem, in SHO n can be 0, and the 0th state, that is the ground state, it is like this. Okay, can be no node. In the first excited there is one node, the second excited there are two nodes, and so on. But what happens here, this shaded area, I mean bluish part left and right, again by same argument you can call it, these are classically forbidden region. Why? Because suppose this is a classical particle dropped inside such a potential well, and as you know the Vx half kx square and x goes up to infinity for both x equals to minus infinity and x goes to plus infinity. Vx is half kx square, so it goes, the potential depth is up and up and up to infinity, right? So naturally it is like almost like the particle in box problem, that if you drop inside some particle of mass m inside this potential well, it can never jump up over the barrier because the barrier height is infinite, right? So there is no way of finding the particle outside this potential. That means this figure outside means this shaded region, right? So there is no way of getting the particle to be able to see the particle here, left side and right side. But interestingly, in quantum case, if the particle happens to be a quantum particle, that means it has dual character, both wave and particle, then what happens? Again, from wave function consideration, we see that outside the box there is a region, it goes extend up to that shaded area, some non-zero psi is there in the first excited still there, the second excited state it's still there. So what does it mean? By same argument, if psi is outside the potential is there, that means mod psi square is non-zero, that means there is some probability density of the particle outside the box or potential well, that means in the classically forbidden region. So again, actually we are demonstrating nothing but tunneling, another example of tunneling. So in SHO case, we again see the tunneling situation. Now here I have given it as a problem actually, that what is the percentage of or probability, what is the probability that you can find it in the forbidden region, what is the probability? Number one question. Number two, is that probability is the same for all n equal to 0, n equal to 1, n equal to 2 and so on. That means for different levels tunneling is possible, but possibly it is to different extent for different levels, possibly, that I have to check. But okay, for the time being let us forget about the second question. Let us just focus on the first question, that just focus on the ground level, n equal to 0. So from the picture itself we can assume that okay, some percentage is there outside the well, but quantitatively what is that percentage? And I suppose that, let me answer the question, that the percentage is nearly 16%. So it is not bad, 16% is too high, right? 0.16 okay, it's negligible, 0.1, 0.2, 0.3, even 1% is okay, very less, but 16%, right? Not a matter of joke. So quantum feature is heavily or very dominatingly visible here. So now the question is how I can quantitatively evaluate it to be 16%. So this is the question, and I am giving a pause to interact with you to some extent. I was mentioning the tunneling microscope, Okay, even I myself don't know that much, but this much I know that it is a quantum gift, particularly gift of tunneling. And the technology people, along with quantum people, engineers, they have devised this sophisticated health or medical instrument. Just I have taken a picture from that book of Engel and Reed. So here it goes like this. So just to show it, to let you know that something like this is there. You don't need to understand the whole steps for your exam purpose, of course not. It just gives a schematic diagram of a scanning tunneling microscope. A few things are there which I don't understand that much. But somewhere, some point tunneling is happening, that is visible from the picture if you see it clearly. Another is a schematic representation of a scanning tunneling microscope. It looks a sophisticated instrument, and here are some image scanning tunneling microscope images of the surface of silicon. So visibly, with open eyes, you don't find this kind of beautiful pattern over the surface of silicon, but if you have a picture with the help of STM, then the images would look like this, right? So that is interesting to see. But this is not only for art for art's sake kind of thing, rather it has some use also. This is another picture of carbon monoxide molecule. Okay, it looks like beautiful capsule like thing picture, but what really they mean I don't know. But we are finally interested that okay, does it really help some way tunneling in real life, real world chemical problems? The answer is of course yes. Some of the reactions, chemical reactions, people have studied and they didn't find any reason of the facts that they have observed, depending on the usual chemical kinetics. Depending on usual chemical kinetics, that means Arrhenius concept and the rest of the kinetics that we know. Some of the observations they could not explain with their usual thermal explanation, Arrhenius kind of explanation. Then they thought of something else, that what really is there going on, and finally they came up with the final solution. Okay, it must be something quantum, we cannot explain with the classical picture. And really people believe now, and they have evidence of course, that of course tunneling of atoms plays a role in some chemical reactions. So here I will show you just one or two examples that people believe that they are because of tunneling only. Otherwise the effects could have been very different had it been only a thermal explanation. So it is not depending on Arrhenius in the sense that tunneling provides another mechanism to convert reactants to products that does not require an increase in energy of the reactants for the reaction to proceed. So that is the usual Arrhenius, temperature dependence, ddt of ln k, that a to the power minus e by RT activation energy concept, etc., etc. But that explanation doesn't work here. It is well known that hydrogen transfer reactions can involve tunneling. An example is the reaction of this kind of R1OH and R2O minus, and that gives you R2OH, that means this H comes from here to there, and R1O minus. So this is called the hydrogen transfer reaction. R1 and R2 are two different organic reagents. Okay. Now, what is the test? Test for tunneling in this case is to substitute deuterium for hydrogen. So it is the isotopic substitution. If you carry out, instead of H, if you take deuterium, then what happens? That because of this change of isotope, what you expect? Not much from classical picture. But if tunneling occurs, the effect is highly significant, appreciable amount, and it decreases greatly. So the amount of decrease they observed because of this switchover from hydrogen to deuterium, that much of decrease they couldn't or didn't expect had it been a simple thermal reaction. But it decreases so greatly that they thought that it must be something else going on over there, and they came up with the presumption that it must be tunneling. So now they explain that okay, if tunneling rate depends exponentially on the decay length that I have already mentioned, decay length, this quantity. Now it is not widely appreciated that tunneling can be important for heavier atoms such as carbon and oxygen. So it is only a proton, right? Proton transfer reaction that is quite legible, that why the effect is so great in terms of tunneling. But the same great amount of effect we are not expecting involving carbon or oxygen atom as such, because in that case, compared to a proton, a carbon atom or oxygen atom is very heavier. That means m is very high for this carbon or oxygen. So if m is quite high compared to a proton, so the denominator part is very high, so the numerator part is very small. So that's why you cannot expect a lot of effect in case of carbon and oxygen. So that could be a small question. Explain why like this. And the second example, that it has been shown that the rate of the ring expansion reaction that is given in the picture is faster than the predicted thermally activated rate by the factor of, you see what big a factor, at 10 Kelvin. So the factor is quite a big, 10 to the power 152. So had it been simple thermal, then the effect, of course the effect is there, that ring expansion reaction, but it should not be that much, but it is really very big because something else, because tunneling. So what is that reaction? Okay, I didn't try to understand the reaction in depth because it's a typical organic reaction, but what attracted me most, that it is saying something very quantum, that other than tunneling you cannot explain the change of behavior of this reaction in terms of the product or reaction rate maybe. Okay, so this is another example. Right now you are equally efficient in organic, physical, inorganic. So this portion you can maybe you can know and you can understand much better than me. But what I am trying to give you, that the particular quantum effect or tunneling effect, an example. So that's all from today's class and the full syllabus. So we may spend a few minutes more regarding some of the points or some comments and remarks you can make, and hopefully we'll come back the next day.